There are three solutions to the situation of case 3. So first, you can discuss with the design engineer to see if he or she can relax the tolerance without affecting the function. So if he can still relax the tolerance but perform the function, then our process capability can still be within the tolerance. The second solution is to decrease the sigma of your capacity, of your process capacity, because currently the process capability, the 6 sigma, is greater than the tolerance. So if we change the process dispersion, if we decrease the dispersion to produce a more peaked distribution, then we can manage to put the process capability within the tolerance. So something you can try is that you can try a new material, you can hire a more experienced operator, or to retrain the current employees, or buy some new machines, and to employ some automatic in-process control. The third solution to case 3 is to shift the process average so that all the non-conforming products occur at one tail of the frequency distribution. We want to move our process distribution to one side because we want to increase the number of products that can be reworked. So even though these products are non-conforming, even though they're exceeding the specifications, but still they can be reworked. So we can still rework on these products and then to make these products to be qualified with some additional man time and money spent on it. And we want to decrease the number of products that have to be scrapped. So these products has to be discarded. They are non-conforming, and we can do nothing on it to make these scrapped products to be qualified. So we want to discrete this portion of products. If the product is grounded from outside, then we want to shift the average to a higher level. Therefore, in this tail, even though they're out of the upper specification level, the specification limit, we can still rework it to be a conforming product. And we want to decrease this tail because if you're manufacturing something with a smaller diameter, you can now rework it to the qualified product. For the products that are produced as an internal member, we want to shift the average of our process capability to a lower side. Okay, because if you have a lower inner diameter, you can still rework it to be a conforming product. But for those with larger inner diameter, you cannot rework them. They have to be discarded. They have to be scrapped. So here's a numerical example for the product specifications. The location pins for work holding devices are ground to a diameter of 12.50 millimeters with a tolerance of plus and minus 0.05 millimeter. So if the process is centered at the mu equals to 12.50 millimeters and the dispersion is 0.02 millimeters, then what percentage of the product must be scrapped and what percent can be reworked? So here's the distribution for the individual values, and it is centered at this mu value, 12.50. So the upper specification limit is the mu plus 0.05, and this lower specification limit is the mu minus 0.05. Okay, so we can identify these specification levels as limits as 12.55 and 12.45. So now I can transform this problem into a statement that is familiar to us in chapter 4. So given the mu and the sigma of this distribution, and given this x1 equals to 12.45, the LSL, and then given this x2 equals to 12.55, the USL, it asks for the percentage of scrapped products, which is equals to the area under the x1. Okay. And then the percentage of reworked products is equals to the area above x2. So to find the area under x1, you first need to compute the standardized normal value associated with x1, given this mu and sigma, right? So this z equals to minus 2.50. And then from table A, you can find what is the area below z value, and that is the same as the area under x1. So that is 0.62% of the scrapped products. Okay, so the computation is not complicated. It's just that you need to extract this information from the problem statement. And for the percentage of products that has to be reworked, it is the same as the area above x2. And because our distribution is symmetric to this central line, to the mu, and the x1 and x2 has the same distance from the mu, therefore the area above x2 equals to the area under x1. So the percentage, so the rework percentage is the same as the scrap percentage, which is 0.62%. The second part of the question asks, how can the process center be changed to eliminate the scrap, and what is the rework percentage? So one thing I want to notice is that the LSL and the USL are set. They are not changing. You are shifting your process. You are shifting the mu value, the average, the mean of the distribution for the individual values. So we want to shift our process to the right, and therefore there will be larger portion of products that can be reworked, and therefore we can eliminate the percentage of product that has to be scrapped, like here. Okay. So now I also transform this statement to the format that we're familiar in chapter 4. So given the standard deviation of our process, and then the x1 equals to 12.45, the x2 equals to 12.55, and also I know that the area and x1 is 0, right? Because we want the 0% of scrap. So what the question asks is, what is the value of the mean? What is the mu that will make the area and x1 to be 0? And after this mu value is obtained, what is the area above x2? So first, to find this mu value, you need to first get what is the z value, the standardized normal value associated with a 0 area below it. So the smallest value that I can get from table A is 0.00017. This is the smallest value that I can get. And then by reversely look up the z value, I can tell that the z value associated with this area is minus 3.59. So I plug in the z value and then the x1, 12.45, and the sigma, the 0.02. So I can solve for the mu. And this mu is solved to be 12.52. So it's shifted to the right with 0.02 millimeters compared to the original process. After we got the shifted mu, the shifted mean of our process, then you can compute what is the area above x2, right? So one thing to emphasize is that you need to insert this shifted mean value here. Okay, you need to use 12.52 as your mu value here, and then the sigma is 0.02, and then use the z to carry the standardized normal value associated with the upper specification limit. Okay, and then you can and then from table A you can tell what is the area under the x2, and then use 1 minus this area, you get the area above x2. And as you can see, the amount of rework is 6.68%, which is significantly greater than the combination of rework and scrap percentage in the original settings. So here's the trade-off. if you want to have a smaller number of scrapped products, then you have to put more efforts for rework. Okay. So that's all for the demonstration of this example.